Good afternoon. This will be day 3 of our modern physics, and we're going to be looking at nuclear binding energy today. I know yesterday I said I'd probably graph uh, the radioactive decay series, but I think I'm not going to bother. I don't think I'm going to worry about that for you guys. That's kind of a basic skill. We all know how to graph, so I think I'm not going to worry about that as a content thing this year. So what I'm going to do then is I'm going to move on to nuclear binding energy, talk about what nuclear binding energy is, and do an example of nuclear binding energy for an atom. Okay, we'll wait for our board to pop up open here. Okay, so what we're going to look at today is nuclear binding energy. Okay, this is day 3, unit 4, modern physics. Okay, and today we have a couple of things we want to do. We're going to be looking at nuclear binding energy. Okay, and we're going to be looking at E equals, mc squared. Okay, Einstein's famous equation for nuclear binding energies. And we're going to do a few examples, if I can find enough, of some nuclear binding energy. So what happened at the beginning of this is what they found was that the sum of all the protons and neutrons of a nucleus, we're not going to worry about the electrons right now, but we're looking at nuclear energy and nuclear stuff, so with just the nucleus. So they said, okay, well, if you take the mass of a nucleus of an atom and get it, and then you take and get the mass of all the neutrons and protons that make up that atom, there's a difference. They are not equal, and that was very surprising. In fact, they was like, okay, well, how is that possible that the masses are different? Okay, and what Einstein called it was the mass deficit. Okay, it says that there is what happened to this mass, and why is it not equal? And he decided that that mass was, in fact, the energy that's used to bind the nucleus together, called nuclear binding energy. And he came up with E equals mc squared to describe how to calculate it. So we'll just do a little summary on that. So nuclear binding energy. Okay. So when we look at the mass of the nucleus of an element, okay, that mass is not equal to the sum of the protons and neutrons masses that make up that nucleus. Okay, so that was the anomaly. Give me a second here. I'm going to get my page up here. Okay, sorry about that. Just getting my page up. Okay, so they're not equal. In fact, there is missing mass. which Einstein called the mass effect, not deficit. Einstein, I guess, has got to have a. There we go. Got those backwards. Okay. Einstein, or this missing mass, is assumed or is theorized to hold or to be the nuclear binding energy of the atom. Okay, and we can calculate this with E equals mc squared. Okay, so that's the famous energy equals mass times light squared, speed of light squared formula. Okay, so we're going to do this manual with kilograms. So we'll do an example with carbon-14, which is a radioactive element or isotope that's used in radiocarbon dating, actually. So we're going to do that one as our example. So okay, so let me set it up here. So our example carbon-14 has a mass of 2.3253 times 10 to the negative 26 kilograms. Okay, so we're going to do this with kilograms. So often you'll see some books will do this with something called the electron volt, which is a particular measure of energy for really small energies. But we're going to do it the old-fashioned way first, and then we'll get into the electron volt and atomic mass unit, which is something that other than kilograms as well. Okay, so we have an example of C14 has a mass of that. Okay, we remember that a proton is remember 1.6726 times 10 to the negative 27 kilograms. A neutron is 1.67 times 49 times 10 to the negative 27 kilograms. Okay, so let's get these scientific notations. Okay, calculate the mass defect. Calculate the nuclear binding energy, sorry. Okay, so the first step in this is we know we have to kind of figure out what the carbon atom is made of. Step one is get the constituents of the carbon atom. So, okay, step one, find the number of protons and neutrons. In C14. Okay, so we know that carbon is 6, so we've got 6 protons and 8 neutrons. Okay, so then we're going to total the mass of the nucleus. So this is going to be 1.6726 times 10 to the negative 26 times 6. This would be 1.6749 times 10 to the negative, sorry, this is 27, pardon me, times 8. Okay, so then step 2 is to total the mass of the parts. Of the protons and neutrons. Okay, so we're going to do that here with our calculator. Be careful you use scientific notation properly. So in our case, 1.6726, scientific notation negative 27, times 6. Okay, I'm going to write these out in steps. You could crunch it down on the calculator if you felt so inclined. 0.00356 times 10 to the negative 26 kilograms. And this one is 1.6749 to the power, or to scientific notation, negative 27 times 8. So if we total those up, okay, we add that one to 1.00356. Don't round anything off, obviously, until you get to the end. You get a total of 2.3438 or 348 times 10 to the negative 26 kilograms. Okay, so now you can see that now we take the lighter mass of the atom and we subtract the atom in step 3 to get the mass defect. Calculate the mass defect in step 3. Okay, subtracting from this one, subtract C14. So C14 was 2.32, what was it? 2.3253 times 10 to the negative 26 kilograms. So keeping this on our calculator, we just subtract 2.3253 exponent, or scientific notation, pardon me, negative 26. And that gives us 1.818 times 10 to the negative 28 kilograms. Okay, that's the mass defect. Okay, that's what we found there. Now we got to convert it to energy by using Einstein's equation. Okay, so step 4, and the final step, is to convert it into energy. Okay, use E equals mc squared. C is 3.0 times 10 to the 8 meters per second. That's what we're going to use. So in our case, this is going to be okay, so we just plug those in. So we multiply by let's see, there we go. So we got 1.6362 times 10 to the negative 11 joules. Okay, so that is the nuclear binding energy of a carbon-14 atom, radioactive atom used in radiocarbon dating of any previously living organism. Okay, and now what we'll look at, we'll also look at this maybe with the electron volt situation as well, once we get into doing a little bit more of the nuclear calculations here. Okay, so that's an example of nuclear binding energy. Okay, let's see if I got another one here for you guys to try. Okay, try this one, and this is where we'll start with the answer for next day. Okay, this will be my last thing, or not my last thing, but my calculation for you to try. So you might want to try pausing this one and then unpausing it after I give you the pertinent information. So try this one. Okay. What is the nuclear binding energy of helium? Four. Helium-4, so like an alpha particle. Okay, let's say that the helium-4 mass, I look it up here, is 6.6443 times 10 to the negative 27 kilograms. Okay, that's all you need to know. Okay, so you should probably give this a try on your own. So pause it, give it a try, and then unpause it, and I'll work it out for you. Okay, so if you've unpaused it, the first step for us is to figure out how many protons and neutrons are in helium-4. So helium-4 has 2 protons and 2 neutrons. Okay, so we're going to go 2 times the proton mass, which was 1.6726 times 10 to the negative 27. We're going to go 2 times 1.6749 times 10 to the negative 27 to get our two masses. So if we multiply those together, we get 3.342 or 452 times 10 to the negative 27. And this one was 3.3498 times 10 to the negative 27. Okay, so then if we sum those, sum of the parts for the nucleus, if we total those two together, is 6.695 times 10 to the negative 27 kilograms. Okay, then we subtract the nucleus weight, the nucleus mass of helium-4. Okay, helium-4 mass is right there. So we're going to subtract 6.6443 times 10 to the negative 27 kilograms. Okay, this is going to give us our missing mass or a mass defect. So this ends up, when we subtract this out, it's 5.07 times 10 to the negative 29 kilograms. Okay, so now that we've got the mass defect, we now take and calculate energy by using Einstein's equation. Okay, Einstein's equation is E equals mc squared. So in our case, 5.07 times 10 to the negative 29 times 3.0 times 10 to the 8 squared. Figured it out, that's just 9 and that's 16. So you work it out and you multiply those two together to get a nuclear binding energy for helium of 4.563 times 10 to the negative 12 joules. Okay. Now, that's a good example there. We did a couple of them. We're going to kind of stop, but before I stop, I want to kind of introduce the unit mass U and the energy unit electron volt to you before we move on here. So when we're talking about atomic masses, rather than going times 10 to the negative 27 times this, times that, times this, they come up with a mass, okay? And they use the little number U to represent that mass. And it's based off the hydrogen atom. Okay, so let's go on to the next page. So at times, okay, nuclear mass and energy units. Are sometimes used. Okay. The electron volt which is usually signified like this, and that equals, there is an energy unit, and it equals, okay, I got to find the constant, I can't remember that one all the time. So 1 electron volt, I got to look it up here because I always forget what it is. Okay, so what we do here is this one here is, I looked it up here, the electron volt is equal to 1.0 So it's just the charge that they have on an electron here. Where is it here? 1.60218 times 10 to the negative 19 joules. Oh, should have known that. I just didn't know the after the 0218 part, because we need to go down to 5 significant figures. 1, 2, 3, 4, 5 significant figures. Okay, times 10 to the negative 19 joules. That's what an electron volt is. Okay, so we'll, and then they use Einstein's equation and they work it backwards to find out what mass would you have if you had 1 electron volt kind of idea. And they work that backwards to get something called an atomic mass unit. So the next thing that they use, the atomic mass unit, which is just a little u like this, is used for mass, for nuclear mass. Okay, and 1 U equals, and we'll do an example like this using these ones as well. What is it here? 1.66 times 1.6605 times 10 and a negative 27 kilograms. So a proton and a neutron are slightly different units, so they're kind of close to what this would be, but not quite, right? And they calculate this using Einstein's equation. But that's what it equals as a constant. So we could actually use these if we use U. Okay, sorry. If we use atomic mass unit and electron volt in our calculation, if we use the atomic mass unit as our unit in our calculations, the energy will result, the resulting energy will be given in electron volts. Okay, so that's kind of the conversion that we use. So let's do a quick example of that here. Okay. Let's see here. Let's get a real simple one. We won't. We'll do it. Well, maybe we'll have to save this for tomorrow. We're almost getting to 30 minutes here. Let's just do a simple example with the E equals mc squared. What is the energy of 1 U particle? Okay, so if we do that one, where is it here? Okay, we have to go. Actually, no, let's not bother with that. This is going to take too long. I'm looking at it here. The exam's going to take us too long. So let's do this next day. And we'll stop at that point because we're getting 30 minutes here and it's going to take us a good 10 or so, 15 even maybe minutes. So we'll do it next day.